welcome to my class. I am Mounika from the Department of Physics, K.B.N College, Vijayawada. Today in this class I am going to explain the second unit of first BSc Physics. So in this unit the main important topic is central forces. So in central force we are going to discuss about the central forces, definition and examples, characteristics of central forces, conservative force, and to prove the central force is conservative force, and proof of central force is a negative gradient of potential energy, and proof of the curl of central force is 0. And coming to the topic last, derivation of equation of motion under a central force and Kepler's laws of planetary motion and their complete derivations. So in this unit we are going to study about all these topics. So these are the important topics in Unit 2. So that is nothing but central forces. So first of all, before going to know all the topics which I have said now, first of all we need to know about the central forces. So in this slide you can see the simple definition of a central force. So a central force is always defined as a force which always acts on a particle or body towards or away from a fixed point and whose magnitude completely depends only on the distance from the fixed point. Here the fixed point, they are saying about the fixed point. This fixed point is also known as the center of force. So, and a central force on an object is a force that directed along the line joining the object on the origin. So this is very difficult to understand. So let us explain by showing this figure. So in this figure represents the central forces very clearly. So in this diagram there are three axes, that is x, y, z. So these are also called as the Cartesian axis also. So in this diagram you can see the point O, which is nothing but the center of the force which is taken as a origin. Origin is nothing but the point where the three axes are joining. Here, so again I am repeating, here O is the center of the force which is taken as origin of coordinate system, and here P be the particle whose polar coordinates are r and theta. So O be the origin and P be the particle whose force we have to determine. So here the central force on a particle P is expressed by one mathematical equation. That mathematical equation is nothing but F is equal to R into F of R. So here we are already saying that P is a particle. So the central force of the particle is nothing but F is equal to R hat into F of R. So here you can see in this slide the center of force on a particle P is expressed by the letter F. So mathematically F can be expressed as F is equal to R hat into F of R, where F of R, here the function F of R is a function of distance. That means R is a distance of a particle from a fixed point. So here R hat is different from R. So I already said R is a distance, but R hat is a unit vector along the radius vector of the particle with respect to that point. So let us see some of the examples. Here the gravitational force of attraction between the two masses. Here there are two particles. The mass of a first particle is m1 and a mass of a second particle is m2. And the force of at particle 1 is F1 and the force at particle 2 is F2. Here you can see the distance between the first particle and the second particle is small r. We already know small r represents the distance between the particles. So here consider particles of masses m1 and m2 separated by a distance r. So the force can be expressed as F1 equal to F2 equal to minus Z into m1 m2 by r square. So here m1 represents the mass of a first particle and m2 represents the mass of a second particle, and r square represents the square of the distance. Here the electrostatic force between the two charges is given by using a Coulomb's law. So by using Coulomb's law we can represent the electrostatic force between the 2 points. What does a Coulomb's law represents? Here you can see force is directly proportional to, here you can see force is directly proportional to product of the two charges, that is nothing but q1 and q2, and it is inversely proportional to the square of the distance. By combining the equations 1 and 2 we will get F is directly proportional to q1 q2 by r square. So in order to remove the proportionality we have to keep one constant, that constant is nothing but k. So F equal to k into q1 q2 by r square. K equal to 1 by 4 pi epsilon naught. Here epsilon naught is nothing but the space constant. We already know, we have used it in a very small derivations also. So the final equation which is given by a Coulomb is nothing but F equal to 1 by 4 pi epsilon naught into q1 q2 by r square. So by using Coulomb's law we can know the electrostatic force between the 2 points. So after knowing about the central forces, these are the some features of some central forces. So the general form of central force is given by F equal to r hat into F of r, where F of r is a function of the distance r of the particle from the fixed point, and r hat is the unit vector along the radius vector r of the particle with respect to that point. So it is clear that central force is a conservative force. So conservative force is nothing but work done by force in moving a particle from one point to another point is independent of a path followed. So that is regarding a conservative force. So these are the additional features of a central force. So under a central force, torque acting on a particle is always zero. So under a central force, the angular momentum of a particle remains constant. So it is clear here the angular momentum is remains constant. So under a central force, the central force is attractive when the function of distance is less than 0, that is F of r is less than 0. So it is represents that the central force is negative. And coming to the second important point, the central force is repulsive when the function of distance is greater than 0, that is positive. So it can be represented as F of r is greater than 0. So we already said that the conservation of angular momentum is constant, so that you can see here. So according to this law, if no external torque acts on a body rotating about a fixed point, the angular momentum of the body remains constant. So according to the definition of torque, tau is equal to dl by dt, that is nothing but r into F. So the ratio becomes 0, dl by dt equal to 0. By integrating we will get L equal to constant, because in the above step the ratio of dl by dt equal to 0. So after integrating dl by dt it will become a constant. So these are some of the examples you can see here in the slide. These are the examples of conservation of angular momentum. The first one is motion of planet in its orbit. So this diagram indicates the planet which is moving about its own orbit. So the motion of a planet in its orbits is the best example of conservation of angular momentum. So coming to the second example for a conservation of angular momentum is scattering of alpha particles by a heavy nucleus. So we already know the central part of an atom is nothing but a nucleus, and the charge of a nucleus is positive. So the scattering of alpha particles by a heavy nucleus is one of the example of conservation of angular momentum. So in this presentation we know about the central force and the basic features of the central force and the diagrammatical representation of the central force and the basic examples of the central force. So these are all the topics which we have covered in this presentation. So thank you.